So today we're basically looking at how gas particles move and just sort of trying to imagine all the things that have to be true about gas particles in order for all of the relationships between pressure, volume, and temperature to be true. And it's also going to help to explain some of the inherent errors in trying to use the ideal gas law to collect lab data. So the first thing we have to understand, of course you want to stop and write this down, is this bit about the kinetic molecular theory. So the kinetic molecular theory is just 5 postulates or stipulations that sort of explain how we want to think about gas particles moving. It's just a way of sort of developing a mental model for how gases move. I generally think about gases moving the way they do in this little simulation that we've looked at before. They're moving around randomly, they're moving around in straight lines, they're bumping into each other, they're transferring energy. And that's really what these little different postulates are saying. First of all, the volumes of gas particles are negligible compared to the space between them, and that really isn't illustrated all that well by this because, you know, obviously if you had a container this size, the gas particles are way, way, way smaller than that. You know, here, if we pause, the space between the particles is many, many, many times, or I should say the particles themselves are many, many, many times larger than real gas particles. And so compared to the space between them, they're much bigger. In real gases, of course, in order for you to have a gas particle this big, represented by this little sphere, your container would have to be thousands of times larger. But that's an important trait to understand about gases. They are much, much smaller in volume themselves than the space between them, which makes them so easy to compress. In other words, to make their volume smaller. The particles move randomly in straight lines. We kind of saw that with the little simulation there. And then the attraction between gas particles is negligible. So we talked about van der Waals forces last semester. Gases have van der Waals forces. They attract each other. But the reason that they're gases at whatever temperature that they're at is because they have so much kinetic energy that it actually overcomes those van der Waals forces. So we say that because they're moving fast enough, and this you'll be able to see if we add heat, you can see it even better, right? The particles are moving so fast that they don't have the opportunity to stick together. So that's why they're gases at, in this case, 600 kelvins. The collisions between gas particles are completely elastic. And you'll get into that more in physics, but essentially it just means kinetic energy is conserved. So when two particles collide, if one is moving, if these two particles are going to collide and this top one is moving faster than this bottom one, then it's going to transfer all of its kinetic energy, and so the bottom one will speed up. It turns out that's not exactly true. We have some sticking that occurs and some loss of kinetic energy as gas particles collide, but it's almost negligible. Okay, and then the kinetic molecular theory also says that the average kinetic energy of particles is proportional to temperature, and that is absolutely true. The higher the temperature, the faster the kinetic energy, the greater the kinetic energy because the particles are moving faster. Okay, so let's get into actually how we measure and even calculate how fast gas particles are moving. We do so with something called root mean square speed, or RMS speed. It's just a measure of speed of particles. So root mean square speed can be calculated, and it's calculated using something called Maxwell's equation. And you don't have to worry about memorizing this. I'll give you this on the test. But Maxwell's equation looks like this. U equals the square root of 3 times R times T over molar mass, which we're going to use big M, little m for molar mass. You'll see it symbolized different ways, but I think that's the least confusing way to do it. So in this equation, U is the RMS speed, and it's going to be measured in meters per second. Okay. We already said that this is molar mass. T, of course, is temperature. It's got to be measured in kelvins. Okay, and the R value here is actually it's 8.31, so it's like our KPA. And I'm not going to really get into too much why that is the same as KPA. It's essentially, if we derive our units, there's a reason mathematically that it matches KPA, but technically the unit for this is not the same as the 8.31 kPa times liters over moles times kelvins. It's actually 8.31 kilograms times meters squared over seconds squared times moles times kelvins. So anyway, this is our R value when we're calculating the root mean square speed for a gas. And so let's look at a problem where we could utilize this equation. It says calculate the RMS speed for an O2 molecule at 21 degrees Celsius. So, excuse me, we're just solving for U. So U equals, and then it's going to be 3 times 8.31 kilograms times meters squared over seconds squared times moles times kelvins. And then our temperature is 21 degrees Celsius, so that would be 294 kelvins. And then the molar mass of oxygen is 32, that's 32 grams per mole. I almost made an important mistake there. If our mass in R, if R has kilograms in it, and we want to get a speed in meters per second, what unit do you think we should have for our molar mass? Instead of 32, it's going to be 0.032 because that's in kilograms per mole. Okay, so hopefully that makes sense. 32 grams per mole would be converted to kilograms by dividing by 1,000, and that's where I get that number, because again we want our units to cancel in the end, and so if I have kilograms on the top, I need to have kilograms on the bottom. So your molar mass will always be just the number from the periodic table divided by 1,000. So see what value you get there. Okay, so you should have ended up with about 480 meters per second, and that's 2 sig figs. If we look at the units canceling up above, kilograms of course did cancel, moles canceled, kelvins canceled, and so I've got meters squared over seconds squared left behind, and then when I take the square root, of course those squared, those 2's go away. So 480 meters per second, pretty fast. If I were to convert that to miles per hour, it'd be about 1,100 miles per hour. So that's pretty close to room temperature, actually a little bit cool for room temperature, and it's still traveling pretty fast. Okay, so we also want to take a look at relative speed of gas particles. So the size of the particles, the molar mass, makes a difference. And that is something that's related by a law called Graham's law. Basically, it says that gases move at a rate inversely related to the square root of their molar masses. So, in other words, if I want to talk about the rate of movement, which is going to be symbolized by R, and I'm going to just be comparing 2 gases. So I'm going to write this as the rate for gas A compared to the rate for gas B is equal to the square root of the molar mass of B over A. So the inverse part, of course, comes with the fact that we've got A on top here and its molar mass is on the bottom over here. So the way that we see these kinds of problems written is talking about gases mixing or escaping from a container. So if you have a puncture in a tire, and the gas particles, of course, are escaping, the speed that they're escaping with depends on 2 things. It depends on the temperature of the gas. So at higher temperatures are moving faster, they're going to escape faster, but it also depends on the size of the gas, because at a given temperature, smaller particles of gas are moving faster. If we go back to our little picture here, if I mix in some light gases, you're going to see that at the same temperature, the little pink ones that are smaller are moving a lot faster, right? So they have the same kinetic energy, but they have a much faster velocity, or rate is what R, we're using R in this case. Okay, so when we're talking about a gas escaping from a container like air out of a punctured car tire, there's a specific name for that. That's called effusion, or just effusion. So this is gas escapes from a container. And then very similar, if you were to imagine like you've sprayed a perfume bottle, so the perfume would have effused from its container as you sprayed it, but then once it sort of is already hanging there in the air, it's going to move throughout and mix with the other gases in the room, and we call that part diffusion. So diffusion is simply gases mixing with one another. So you've already got some gases in the room, you spray some perfume, and then the perfume evaporates, and that gas diffuses and mixes with the other gases in the room. And the rate, of course, depends on its size. So if we want to compare two gases, we can come up with a relative rate of diffusion for two gases. So let's say we're asked a question like, how many times faster does helium effuse compared to nitrogen? And the Graham's law equation works for both effusion and diffusion. It doesn't know the difference between the two. So it's just going to be R of gas A over B is equal to the square root of the molar mass of B over A. Okay? So how many times faster does one effuse than the other? We already know that the helium, which is only 4 grams per mole, and we can use grams now because we're not specifically using an R value that dictates that we use kilograms. And nitrogen is going to be 28 grams per mole, pretty close to exactly. We know that the helium is going to be faster because it's much lighter. So the question is, how much faster? So the way that we do this is we're trying to solve for an unknown rate. And that unknown rate, probably the easiest way to do it is to think of the slower, bigger gas. We're going to assign a rate of 1. And it doesn't matter which one we make A and which one we make B, but mathematically it's maybe a little bit faster to have the unknown, we'll call it X, on top over here on the left. And that's going to be rate A. So in this case, A is helium and B is nitrogen. So nitrogen's relative velocity is just going to be 1, because the answer to the question is going to tell me how many times faster helium moves than nitrogen, and so X is going to be a number greater than 1. So I just have to make sure that I understand and maybe make a note of the fact that this is helium and this is nitrogen, and when I go to the other side, the helium molar mass goes on the bottom. So helium's molar mass is 4 grams per mole and nitrogen's is 28 grams per mole, and so then I just have to solve for X. So give that a shot. Okay, and there you go. So you see that helium effuses 2.6 times faster because X turned out to be 2.6. So it escapes from a container, or even mixes with other gases in the room, if we were talking about diffusion. But in this case, we're talking about effusion. Either way, the number is 2.6 times faster. So, for example, if you had a helium balloon, it deflates so quickly, if it's a rubber helium balloon anyway, because helium atoms are moving that much faster than nitrogen molecules. Whereas, if you just fill up a balloon with air from your lungs, that's mostly nitrogen. So that balloon's going to stay inflated longer than a helium balloon because the nitrogen is moving so much slower.